All right, so let's keep pushing neutrinos. I think by the end of today, you'll probably be fed up with me. It's been a lot of neutrinos. There will be 2 lectures today. So let's try not to kill each other. So here's the deal. We have been talking about, MEV, GeV neutrinos for oscillations and all that. There was the colloquium, which was mostly on that as well. And I think we're done with that. So let's change the energy. Let's talk about something different. So in the lecture today, I wanted to talk about astroneutrinos and cosmogenic neutrinos. So here's the deal. Neutrinos created in the cosmos, they do offer a probe of extreme environments. So what do I mean by that? For example, if you have a supernova, the first thing that comes out of the supernova are neutrinos. And actually, 99% of the supernova energy is lost in neutrinos. Or if you have a, a gamma ray burst, or extreme astrophysical environments where you accelerate cosmic rays and so on and so forth, neutrinos will offer an excellent probe of these environments. Mostly because charged particles gets deflected on magnetic fields in galaxies, and photons can, at high energies, can scatter on the cosmic microwave background. So at very, very high energies, the only particles that propagate kind of in a straight line, or in the geodesics, and does not interact are the neutrinos. Besides that, there is actually something which I am not an expert on that, but it's very interesting. We do not actually know the mechanism of acceleration of cosmic rays. There are many ideas, cosmic rays. There are many ideas of having shock waves and charged particles bouncing back and forth and getting more and more and more energy. But none of these ideas are like spot on. Some of them you cannot get to very, very high energy, so you can explain part of the cosmic ray spectrum, but not the entire cosmic ray spectrum. Some of them require modeling and assumptions that maybe are correct, maybe are not. So the idea is that by studying the sources of cosmic rays, not only with photons and protons, etc., but also with neutrinos, can give you some hints of what is the source of the ultra-high energy cosmic rays. Besides that, very, very high energy cosmic rays above what is called the GZK cutoff. So the GZK cutoff is essentially when cosmic rays get so energetic that the universe is not transparent to them anymore. They will interact with the cosmic microwave background. Neutrinos will not do that. So at some energy, it is expected that neutrinos will be the dominant source of cosmic rays at some very high energies, or at least that the cosmic rays that started above the cutoff and interacted with a cosmic microwave background, they will be a source of ultra-high energy neutrinos. We have never observed neutrinos at this energy, so typically these energies are about 10 to the 19 electron volts. The highest neutrino we have observed until 2 weeks ago was about few PeV, where PeV is 10 to the 15 electron volts, right? We have never seen this. There was a talk 2 weeks ago by the KM3Net experiment on the Neutrino 2024 conference. And they do have the most peculiar event, although this is still super preliminary. So I will not offer a conclusion of that story for you. But the KM3Net well, let me talk about KM3Net later. Let me just do a few more things, and I'll talk about observatories in this event on KM3Net. The last thing that I want to say is that ultra-high energy neutrinos, because they are what I would call extreme physics, right, very high energy, they are a good window to beyond standard model probes, okay? So think about it. On one hand, we are seeing neutrinos at IceCube, for example, and I'll tell you details about the experiments in a second, at the PeV energies. LHC is a 14 TeV machine, so this is 100 times more energetic than the LHC. Of course, this is not, it's a bit of an unfair comparison, because the LHC is 14 TeV proton-proton. So the center of mass of the interaction is 14 TeV. Here, a neutrino is at the PeV, but it's hitting a proton at rest. So if you calculate, the center of mass energy is actually about the 10 TeV scale. There are a few more details on that, because if you remember, when you have proton-proton collisions at the LHC, what really, really matters is the S hat, the center of mass of the partons, and that is typically well below this 14 TeV. It's maybe at 1 TeV scale usually. There's a whole distribution, all that. Because the two protons are composite particles, you can take a quark or a gluon from each of them, which carry a fraction of their momenta. For these neutrino-proton collisions at very high energy, it's slightly different, because the neutrino, as far as we know, is elementary. So the neutrino energy fraction is 1. And then you take a parton from the proton. So you pay the price of the momentum fraction only on one side of your, your interaction. But still, the comparison is that the center of mass energies for these ultra-high energy events is comparable to the LHC. So I'm not going to go into cosmic ray physics. I'm not the best person to talk about cosmic ray physics for you. But I will tell you about the phenomenology that we can do with neutrino observatories, okay? So a typical neutrino observatory is this. Not all of them are the same, but a typical one is this. You deploy a string with PMTs, photomultiplier tubes, right? So the goal is that you will detect the light emitted by charged particles that traverse the medium on these PMTs. This is the case for things like IceCube, where the strings are deployed on ice in the Antarctic. KM3Net. KM3Net is essentially IceCube, but melted in the Mediterranean Sea. And you might ask yourself, you put this stuff in the sea, but what about fish and all that? It's okay. It's actually okay. Fish don't do much. I mean, these strings are not like a little string, right? They are decently a solid thing. It's not like a fish is going to touch on this and this is going to like. So there are studies about fish, yeah. These detectors are actually so special that like gazillion years ago, some volcano erupted. Don't ask me the details, before my time. Because this volcano erupted, there was a cloud of like debris and ash in the sky and all that. And you can actually see that in the ice in Antarctica. There is a layer in the ice which has a lot of dust. And some of the properties of this dust layer has been better understood by IceCube than whatever we did before that. So these experiments are like amazing, right? And now there's like studies of fish and Right, on bioluminescence. Yes, yes, yes. So there is a lot going on here. But for neutrino physics, it suffices to say that fish are not a background for neutrinos.
Test. My problem with KM3 is not even the fish, it's the current. Because in ice cube we have ice is fixed, but in the Mediterranean these strings are like kilometer long,
Yes.
and you have a current, and the current changes with the depth in the sea. So how do you account for that?
Well, they account for that. I don't know exactly the details on how they take care of that in practical terms, but it does work. They do have maybe 20 strings already there. They are taking data. So I guess you do have the currents, but also these strings, they're not like a little piece of rope, right? They are like a solid thing. I mean, they're not rigid, but they're also not super duper flexible, right? So it does work, and there are many, many smart tricks that I know that the experimentalists play on this thing. Like, for example, on these PMTs, they also have LED lights, so that they can shine the LED light, detect on the PMTs in the experiment, and know the position of every single PMT there, and do calibration, so on and so forth. So there are several tricks you can play to account for this kind of stuff. But next week we'll have experimentalists talking about neutrinos. He might give a better answer than I can.
It's kind of a equilibrium, right? Because in water you have a higher resolution, in ice you have actually in the sea, in the water you have a higher resolution, in ice you have a lower resolution, but because of this current movement, you probably lose a little bit.
Well, so I don't know about the details of the current, but the propagation of light in water and ice is actually fairly different. So there are two main things: that light can be rescattered and light can be absorbed. On ice, light is absorbed less than in water. So ice is more transparent in some sense than water. But on ice, light scatters more frequently. So what happens is that when you have, for example, a muon traversing your detector, and it's emitting light, this light will start rescattering and diffuse in a way. And this diffusion in ice is actually a more important process. So the tracks on ice, they are a little bit more diffuse versus the tracks on water, which are more like really tracks, are more like, let's say, a better resolution on this track. But then on the flip side, ice absorbs less light. So on water, this light will get absorbed faster, although it doesn't get rescattered so much. But it actually happens that there are several advantages of doing that on ice or on water for different physics. So it's just a slightly different experiment, if you want. All right, so how do you see neutrinos here? Again, Cherenkov light, we want particles faster than light in water. Muons, you do something like that, so muons will leave a track on your detector. Electrons, photons, and hadrons, they will interact very, very, very quickly and shower. So whenever you have an electron, it will shower into stuff, and then the emitted light will be way more isotropic. So we call this thing usually a track, and this thing a shower. So these are the two main building blocks of how events look like in detectors like IceCube and KM3net. There are a few other things that can happen, which are built from this. And maybe the most interesting one is what they call the double bang events, where a neutrino comes, it creates a tau lepton, and usually when you create a tau lepton, you hit some hadrons and you get some hadronic stuff there. So the hadrons shower very quickly and give you a shower. But then the tau lepton, it is very short-lived, but if you boost it at, say, 100 PV of energies, it can actually propagate like 100 meters-ish, and then decay. So this guy will propagate, and then it will decay, most likely to hadrons, which will give you another shower. So that signal of shower, it's called a double bang, one bang, two bangs. And that is typical of very high energy tau neutrinos. In principle, you can use that to identify tau neutrino events in IceCube, for example. Of course, this only works if the tau is quite energetic. If it's not, it will decay very shortly. The two bangs will be on top of each other. You can't see it. And although I'm telling you about, like, I drew two bangs that you can see the difference on your eyes, like geometrically. Experimentally, the time of arrival of light is actually more important than where the light got for these bangs. So what you see is a double bang signature on the time spectrum of the light yield on the PMTs. So tracks allow you to do muons, essentially. Only muons give you tracks to first approximation. And showers are electrons, photons, hadrons, and double bang, like tau, at high energy. Low energy taus will either do showers most of the time, or sometimes the tau can decay to a muon and give you a track, right? So sometimes you have a tau here that decay to mu, nu. It's kind of 10% chance.
Sorry, I don't know too much about IceCube and other observatories. Usually they are kind of no nível do mar, in the sea level.
No, they are deep. They are deep. Yeah. So imagine that this is the ice floor.
Mm-hmm.
You put strings here, but you only put PMTs like very deep in the ice. And the goal of that is that if you put things on the surface for neutrino physics, life gets real hard because of cosmic rays and backgrounds.
But isn't that kind of bad, because the muon and the tau are too heavy and they decay really quickly? So
muons don't decay. Well, sorry, muons do decay. For neutrino experiments, muons don't decay.
So you're going to find the muons that came from
you got muons from neutrinos, but also from cosmic rays.
Yeah, cosmic rays. Okay.
Yeah. So this is a very important thing, actually. Muons are unstable particle. That is a true statement. But whenever you're thinking about experiments and observables, you got to think about the time scale of your experiment or your data taking or whatnot. And for these things, IceCube most likely will never observe the lifetime of a muon. Because if the muon has, say, 1 TeV of energy, its lifetime, so the muon lifetime is what? Does anybody know the muon lifetime?
I don't know, some seconds.
Is it 2 microseconds? Is it 2.2 microseconds? Am I right? Is that 2.2? Yeah. So 2.2 microsecond. If you boost it, you get this. So you get energy over mass of the muon times the lifetime of the muon. Let's take, so the muon is 100 MeV. Let's take 1 TeV as energy. So 1 TeV, 100 MeV, times 2.2 microsecond. This is what? There are 6 order of magnitude minus 2. There are 4 order of magnitude, so that's 2.2 times 10 to the minus 2 seconds, okay? But the muon travels at the speed of light, right, at these energies.
But,
So
but
the gamma c tau, the distance the muon travels before decaying, will be 2.2 10 to the minus 2 second, 3 10 to the 10 centimeter per second. So that gives you about 6.6 10 to the 8 centimeter. I can't do centimeters, so let's do kilometers. There are 5 orders of magnitude here, so 3 kilometers. 1,000 kilometers. So 1 TeV muon will take 1,000 kilometers to decay on average. That is to say, muons for ice cube are stable particles. They will never see a muon decay. Maybe they will, but it's very unlikely. This is the same for like dune, for SBN, for all neutrino experiments. To first approximation, muons are fairly long-lived.
okay, great. Thank you.
Taus are not, right?
Okay.
You can do the same calculation for taus, and you'll see that if you put 100 TeV here, gamma c tau will be of order 100 meters or so.
Okay, but the moon travels kind of 99% of the light speed?
Yeah, it's one. You
Okay.
know, yeah.
It's
V
not,
equals
because
C.
it has mass. So, okay, well,
Yeah, but you know, anything below 0.1% for me is 0. So at least for this talk. Actually, for this talk, anything below 1% is 0. And anything below 10% is almost 0. Because it's a question of like how well they can measure stuff, right? If you have a super precise experiment that can measure things below the percent level, should care about percent level effects. But if you're measuring things at the 10%, you really don't care about the 0.1% effect, right? All right, so the shape of the events will tell you the flavor of whatever happened, of the neutrino that caused that. It's a bit more complicated than that, because in usual neutrino experiments like DUNE, in accelerator experiments like DUNE, most of the time a neutrino comes, interact within your detector, and then you see the muon created out of nowhere. Here, because this thing is not like contained, it's just strings in the ice, the neutrino could interact outside, create a muon that actually comes from the outside. It comes from the outside, and it leaves the detector. So these are through-going muons. You can have contained muons, you can have through-going muons, muons that started here and left the detector. And this makes phenomenology slightly more complex. There are ways for you to reduce the background from cosmic rays, but I don't care about that right now. Just believe that you can reduce these backgrounds. So now, if you look at the topology of the event, you can get the flavor of your neutrinos. And why do you care? Why do you care about the flavor of the neutrinos? Because I told you that we don't know the mechanism for accelerating cosmic rays. The flavor of the neutrino can actually, in principle, give you something about what decayed to the neutrino, so what actually got accelerated in the first place. For example, imagine that I have an astrophysical environment in which I produce very, very high energy pions. These pions will always decay to mu and nu mu. And then this is going to be followed by possibly a muon decay to this. So the flavor composition of a source that accelerates pions would be something like, let me just write this, 1, 2, 0, where this is nui and anti-nui, nu mu and anti-nu mu, nu tau and anti-nu tau. So your source will give you something like 2 muon neutrinos or antineutrinos for each electron neutrino. Maybe the environment absorbs these muons before it decays, or like pushes the energy down somehow. And then you would not get a 1, 2, 0, but you would get a 0, 1, 0. Or maybe you have more exotic stuff, like a combination of pions which decays to muons and muons that get absorbed, and some muons that don't. So you'd get a combination of 1, 2, 0 with 0, 1, 0, and so on and so forth. So if you understand the flavor composition of these ultra-high energy neutrinos, you might be able to say that it looks like pions have been accelerated. Or maybe it looks like you accelerated protons that generated pions, and then this pion decay to neutrinos, and so on and so forth. So there is a lot of interest in discovering the flavor of these ultra-high energy neutrinos. But of course, this is the flavor in the source. So how would we calculate the flavor at the Earth? So we can do this. The flavor, well, let's do this. Imagine that you have a source which emits some neutrinos of flavor alpha, but these sources are very, very far away, okay? In fact, we have seen several of these ultra-high energy neutrinos. Tracks have excellent pointing capabilities. So you look at the direction of the track, and you see if there is something there. Just look at the sky map, and is there an object there? And what we know for sure is that these cosmic rays, the majority of them are not coming from the galaxy. The galaxy has a plane. We can see the galactic plane in the sky. And if most of these ultra-high energy neutrinos would come from the galaxy, you would see an excess coming from the galactic plane, but you don't. You actually see them essentially isotropically. So this is a strong evidence that these ultra-high energy neutrinos are not galactic. They are extragalactic. That means that they're super far. So imagine that you produce some neutrino alpha. It takes so long to get to us that we will decohere into neutrinos I. And you might start like seeing some similarities with solar neutrinos here, right? And then these neutrinos I get to us, the neutrino mass states, and when they get to us, we detect them as mu neutrinos or tau neutrinos or electron neutrinos. So we need to see what is the probability that a neutrino I is detected with flavor beta. So the flavor of detection, the probability of producing a neutrino alpha and detecting a neutrino beta for these ultra-high energy neutrinos is going to be the flavor composition F alpha. So that would be this, always normalized to 1. So it would be, for example, 1/3, 2/3, 0, times the amount of nu I in neutrino alpha, and you sum in I, times the amount of nu beta for the detection in every neutrino I. So you are summing on the flavor of the source, you're summing on the flavor that decoheres, and then you get your detection here. What does that mean? That means the following. Remember that the PM&S matrix goes like, if I put the modulus here, goes like maybe a modulus square, 0.6, 0.4, 0.02, 0.5, 0.5, and these are like order 0.5, 0.4 numbers. There is a big uncertainty on these guys. So because the PM&S matrix is essentially democratic except for one entry, it doesn't really matter what's the composition at the source. If these numbers are always close to like 1/3, 1/4, half, even if you start with something extreme like 100, you are going to throw this nu in all the other neutrinos. So no matter what is the flavor composition of your source, you always want to be in the middle of what we call a flavor triangle. What is a flavor triangle? You put here electron flavor, muon flavor, tau flavor. The ticks go like this, for example, like that, and like this. It's not an easy plot to draw in the blackboard. And if I start with, for example, 100, so all neutrinos are electron neutrinos, I am here. So this is 0 to 1 on electroneutrinos, 0 to 1 on muoneutrinos, 0 to 1 on tau neutrinos, okay? So I can start in a point here on the source, but because of the propagation and because PMNS matrix is essentially democratic, this will be thrown to the middle of the triangle. So you can actually, and this is an exercise, this is a fun exercise. Drawing this plot is highly non-trivial, but it's a solved problem on Stack Exchange. Mathematica and Python. And I know from experience. You can actually do this exercise. You take a specific flavor composition. You take the best fit values of mixing angles, and you calculate where you are here. And then what you do is the following. You can vary the flavor composition and start to draw like a region in this triangle plot. And you can vary the uncertainty on the mixing parameters given, I don't know, maybe 2, 3 sigma. And that will draw a region which is like a dog bone region. Maybe smaller than that. Maybe like this. So no matter where you can start here, you can start there, you can start here. You're always thrown kind of to the middle of it. It's not at 1/3, 1/3, 1/3. So there is some hope that you can actually do something there. But you're always kind of in the middle. Go ahead. Nessa. Okay, so why are we summing on alpha in this equation? Because this is the flavor at the source. So at the source, I can produce, let's say, electroneutrinos or muoneutrinos. So I need to sum up all neutrinos that I produce at the source. So for every electroneutrino that I produce at the source, I get some probability of detecting with some flavor beta, but also for every muoneutrino and for every tau neutrino. So since I cannot pick what the source produces, I need to sum up on the source, on the flavor distribution of the source. Yeah, sorry. Yeah. This is beta only. Is the probability of detecting a flavor beta given a specific source distribution. Good, thank you. Any further questions, comments? All right, so currently, by leveraging the event topology, IceCube puts a constraint on this. It's like here. It's not like whatever is inside is allowed. You know, it's not great, but it's also like ruling out BSM physics. And in the future, IceCube might actually be able to do something like fairly, this would be future. It might be able to start to like distinguishing where you are in this region. Now, let's try to connect with what we discussed there. As I told you, this is like extreme physics, and extreme physics is a probe. Oh, that's fine, that's fine. So currently, by looking at tracks versus showers, IceCube can put a constraint on the flavor triangle, which rules out all the extremes. It still is not very sensitive to what can happen, but it's ruling out the extremes. In the future, for IceCube Gen 2, for example, if they put more strings and all that, they'll get way more events, they'll get better, well, essentially more statistics, and this will allow it to shrink this flavor triangle to a small enough region, which may allow you to distinguish the production at the source. Because a 100 production may be mapped like on this region here, a whatever production may be mapped on this region over there, and then, so if you shrink the zero bar enough, you might be able to distinguish the flavor of the source.
I have two questions. First of all, can you explain again why we are going to the center of the triangle?
if these matrices were essentially 1/3 in every entry, it doesn't really work because it needs to be unitary, but whatever. Let's just say 1/3 in every entry. It doesn't matter what you start here. You always get 1/3 in each new I. And then you get to 1/3 in each new beta. So if this was truly democratic, that is, every neutrino is an as democratic as possible sum of mass eigenstates, no matter what you do in the source, you always predict the same number of nu e, nu mu, and nu tau in the detection. Because you're not exactly democratic, like 0.6 is not 0.4, and there is an almost zero entry, you don't really get to that level, but you still get very close to 1/3, 1/3, 1/3.
So this is a consequence of going to the mass eigenstates. I mean, the neutrinos are going to the mass eigenstates, or not?
It is a consequence that you are decoherent to the mass eigenstates, and it's a consequence of what neutrino mixing is, what nature chose for neutrino mixing. If theta 1,2 was 5 degrees, and theta 2,3 was 10 degrees, and 1,3 is whatever it is, this matrix could have been very close to like diagonal with small entries of axis, of diagonal. And if that is the case, if you start with a nu 2, for example, you have very little nu e, you have very little nu 2 and nu 3 on it, so you have mostly nu 1. And a nu 1 is mostly nu e. So if you start with a 1, 0, 0, you might end up with a 0.9, 0.05, 0.05. You know, like this could have happened, but nature said, nope, not in this universe.
Yeah, okay.
So because the mixed angles are what they are, you end up always close to the middle of the flavor triangle.
Okay. The second question is, oh, thank you. You answered my question. The second question is, what you'd bring to you if you know the amount of neutrinos and the type of neutrino produced at the source?
So one thing you could imagine is that if you have a mechanism that accelerates cosmic rays in a source, it should accelerate charged particles in a dense environment. And very energetic charged particles do like to interact quite a lot. So you might have lots of production of mesons. And it just happens that whatever you produce that is not stable, well, almost whatever you produce, will decay to neutrinos. Pi pluses and minuses decay to neutrinos. Well, pi zeros don't. Kaons decay to neutrinos. Muons decay to neutrinos. Taus decay to neutrinos. So whenever you start producing lots of mesons, you will get a big neutrino flux. So understanding the flavor at the source may help you understanding what is the mechanism that accelerate cosmic rays. It is not a trivial connection. It is not like, oh, it's a nu mu source. Therefore, no, it's not that simple. It's way more complicated, but it's one invaluable piece of information that will help you understand the flavor, the cosmic ray acceleration mechanism.
Okay, great, thank you.
All right, any further questions? So let's keep going. Okay, so so if you have some time, try to plot a flavor triangle. It will, and you can even play with mixed angles. You can play with mixed angles at their measured values, and you can like go crazy, right? Say, what if theta 2,3 was actually 0, and this thing will start like going away from the middle. There's also lots of interesting stuff that, for example, if you had some beyond standard model physics stuff, for example, imagine that neutrinos are unstable particles, and imagine that they decay. So you could imagine a universe in which every nu 1 and 2 decay down to a nu 3. So now you produce a flavor alpha in the source. It decoheres to nu 1, 2, and 3, but this nu 1 and 2 will decay. So you end up with only nu 3. And then to detect a nu 3, let me not do nu 3. Let me do nu 1 and 2 and 3 decay down to 1. I think that's easier for me. Nah, maybe I should do the Neutri. That's fine. Let's skip the Neutri. Sorry. So this thing comes down. This is Neut3. Neut3 has no NUI on it. So if neutrinos 1 and 2 would decay away to Neut3, the flavor would be 0 electron neutrinos and about an equal amount of mu neutrinos and tau neutrinos. So, is that right? Yeah, so like 0, it's projected down here. So this is already ruled out, I believe. In the future, you can put stronger constraints, but this is something like these flavor triangles can teach you about the stability of neutrinos, for example. Now, there is one more thing I want to say in my last minutes, which is a very interesting way of detecting the neutrino flavor, not by doing tracks versus showers, but actually by doing statistics. And this is the way. At very, very high energies, and remember, we are talking about PeV here, you can actually scatter on an electron and produce an on-shell W boson. What does that mean? A NUI bar comes here and scatters on an electron in the ice, and the energy is so high that you produce a W boson at its mass shell. That means the following. When you calculate this thing, let's just put, I don't know, it can be, what do I want? Let's just do quark bar. Maybe not quark. Yeah, it doesn't matter. So you produce this guy via, you scatter on this guy via W and produce quarks. If you calculate this amplitude, remember, 1, 2, 3, 4. We go against the arrow. U1 bar, that's the spinor. Coupling, there are couplings like G over 2. So this is a G over 2, I think it's this. G over 2 gamma mu PL. Where G is the electroweak SU2 gauge coupling. So you get a G squared over 4. We should check the factors of 2. Gamma mu PL U2. Then you get the propagator, G mu Q mu Q nu over MW square, where this is Q. Q square, and remember, well, let me just do Q square, MW square. And here I actually need to add one more piece, because if I don't, it's going to get ugly, which is the width of the W. And then down here, you got your U3 gamma nu PL U4. This is a number. This is a number. These are just numbers with Lorentz indices, okay? So what is the deal about this cross-section? Q, in this case, is P1 plus P2, which is actually Q squared is S, the center of mass energy. And this is why we call this an S channel, right? Because Q is S. So we can write this Q squared here as S. So if my center of mass energy is equal to the mass of the W, this is canceled out. And this is on the denominator. Canceling denominator is great, because then the whole thing pumps up. And this is actually why I need to be a little bit more careful here at the width of the W, because if I don't, this is going to be a 0, and I'm going to get an infinite cross-section, and that doesn't make sense. So let's see at which energy we actually get to produce an on-shell W. Usually people call this as a glacial resonance. And the reason is just because Glacial published a paper, the first paper, suggesting that this process could be interesting. But it's essentially an on-shell W production. We call it on-shell because S equals MW squared. So what is S? Neutrino comes, oops, with energy, 0, 0 energy. That's the neutrino for momenta. And you have here an electron, mass of the electron, and a 0. So S is P1 plus P2 square, P1 square, 2 P1 P2 dot P2 square. P1 square, that's the mass of the neutrino, known to be 0 for this. Right, it's not 0, but for this is 0. P2 is the mass of the electron. Honestly, if the electron mass is relevant here, like, it would be great to be able to see the effect of the electron mass. That's 0 also. P1 dot P2 is here. E nu mass of the electron. That's essentially S. I'm dropping terms below the 0.1%. And we want this to be equal to the mass of the W. So the energy of the neutrino needs to be mW squared over 2 mass of the electron. And let's plug in numbers, right? The W is, what's the mass of the W? Mass of the W is something that you need to know by heart. 80 GeV. So you gotta know your bank account password, your mom's birthday, the mass of the W, the mass of the Z, G Fermi, and the mass of the Higgs. The rest of the stuff is a plus. You get it eventually if you use enough, but this is mandatory. You gotta know the mass of the W and the mass of the Z. So the mass of the W is 80 GeV, and I'm actually not kidding. If you don't know the mass of the W by heart, your life's going to suck, right? You gotta know the mass of the W. 80 GeV squared, and electron mass, I assume everybody knows, half an MeV. Twice half an MeV is 1 MeV. 8 square, 64, bunch of zeros. This is 6.4 PeV. So at 6.4 PeV, we get an enhancement of the cross-section, of the naive cross-section, by canceling this. The usual cross-section will have mass of the W in the denominator. That's the amplitude. When this is like G Fermi. When we square, this goes like 1 over mass of the W to the 4th. But this cross-section, because you're on resonance, this cancels out, and this becomes, when you square, mass of the W squared times width of the W. Now, what is the width of the W? That you don't need to know by heart. I don't know by heart, so I never use it. The width of the W is obviously 2 GeV. How can we not know that? So the width of the W is 2 GeV, which allows me to do this. The glacial resonance cross-section with respect to the usual, let's say, charged current interaction not at the W pole, this ratio is essentially, this guy here will go like 1 over mass of the W square, width square. This guy here is 1 over mass of the W to the 4th. 1 over, so we cancel that, and this enhancement is about mass of the W to the 4th, square, over width square, and this is 80 GeV over 2 GeV square, 1600. So we got a factor of 1,000 enhancement on the cross-section. This is not a joke. This cross-section is so big that when you compare that to like a usually much, much, much larger cross-section, which is deep inelastic scattering. Deep inelastic scattering, you are scattering on the quarks of the proton and neutron, and this you're scattering on electrons. When you compare with deep inelastic scattering, what you get, something like this. This is energy. This is 6.4 PeV, and this is cross-section. Deep inelastic scattering goes like this. The cross-section electrons, this is on a log scale, it goes like that. actually goes down. So at the peak, this cross-section it beats DIS. And it only happens for new E bars, which gives you now not only a statistical, because like it's not an event per event thing, it's just at this energy, most of the events you see will be from new E bars. Not only tells you that this is a new E, well, bar, but it's an anti-neutrino. There's nothing else on IceCube that can distinguish neutrinos from anti-neutrinos. To first approximation. There's one small thing that could help you distinguish neutrinos from anti-neutrinos. Do I still have 1 minute or 5? So, yeah, okay, so before I go there, this cross-section is enormous at the resonance. Of course, when you integrate, it's not actually that super duper large, because as soon as you go off resonance, it goes down real quick. But at the resonance is actually pretty good. So this is one of the best ways to distinguish neutrinos from antineutrinos in IceCube at that specific energy. If you go to different energies, there is still a way to distinguish neutrinos from antineutrinos, but it's not very obvious. The way to distinguish is that if you calculate the Feynman diagrams and the cross-sections for neutrinos and antineutrinos scattering on quarks, you see that there is a different helicity structure. That is to say, one of these things will have a PL, the other one will have a PR, if you want, or it will be like flipped. So because of these different helicities, the amount of energy a neutrino gives to a quark tends to be different from the amount of energy an antineutrino gives to a quark in deep inelastic scattering. We call that the inelasticity. The inelasticity is the amount of energy that you give to the hadrons. So it's usually people use a Y for that, which is what is that? 1. I can actually just do this. It's E. I don't want to do E nu out. So it's, is that it? E nu hadrons over E nu. So let's see. If all energy goes to hadrons, maybe it's just this. I gotta check. So, okay, exercise number 17. Check this. I think if inelasticity is 1, all the energy goes to hadrons, so we probably don't have that. If inelasticity is 0, then it's elastic. That's the only thing that makes sense, right? But still check that. The point is, antineutrinos tend to give, oh yeah, because I think people put the mu on here. 1 minus that. Yeah. If all energy goes to the lepton, then it's an elastic scattering. It's 1 minus 1, that's a 0. If no energy goes to the lepton, then it's super duper inelastic. The Y goes to 1. Antineutrinos tend to give more energy to the lepton. Neutrinos tend to give less energy to the lepton. So if you look the inelasticity distribution of your events, you can statistically separate a sample that will be neutrino-rich and a sample that is antineutrino-rich. That's the best you can do. So, yeah, I think this is all I had to say for today. Actually, for the whole lecture, well, forever, because I'm not going to go back to that, about ultra-high energy neutrinos. So I hope you got a feeling of why this is interesting. Any questions, any doubts? So when neutrinos interact with quarks, what you have is this. You have a neutrino comes. It exchanges a W boson. You have a proton here, which I'll depict as a blob, which has quarks inside it. Maybe I should do this. Like, usually a proton has up, up, down. That is what we call valence quarks. as you go like into higher energies, you can create pairs of quarks, antiquarks. So you can get something out of proton, like, for example, a strange quark, and scatter on this strange quark. It goes out 2 quarks, but then when it does that, you actually need to come up with some way of hadronizing. Usually this is not a super trivial thing. It's non-perturbative, so there are several like empirical models. But the way you calculate deep inelastic scattering is essentially this. You take what we call a PDF, a parton distribution function, which describes how much momentum the specific quark that we're interested in carries from the entire process. So the PDF gives you the fraction of momentum of quark or parton, let's say Q or G for the gluon, right? So this is, it's just a weak interaction, but you require a little bit more work because now you are breaking the proton. Does that answer your question? Cool. Too late.
Can you repeat what you said about neutrino decay? The only one that is ruled out is nu1 to nu3 if it's inverted ordering?
Well, so if nu1 and 2, if it's inverted hierarchy, decay to nu3, this is a nu3. Nu3s have no nu-e's on it, so there's nu-e, nu-mu, nu-tau.
Ah, okay.
And that puts you down here. But if it's the opposite, if it's 1, 2, 3, and 2 and 3 decays down to 1, it kind of happens that nu1 is like 0.2, 0.2-ish. It's not precise. You are still kind of in the middle of the triangle, so you might be, so there is like lots of nu-e and a bunch of nu-mu and nu-tau, so you might be like here, maybe. So, you know, this is not very easy just because of the structure of the PMNS. The other one is much, much easier because theta 1,3 tends to 0.
Yeah, so for the other case, if IceCube can determine the source and we kind of infer its distance, how well is the bound on the neutrino mass from the lifetime? Because
well, so it's complicated, right? Because you have a mass, but you also need a mechanism. Within the standard model, neutrinos could decay, right? If you have a nu I, a nu 3, it could decay to nu 1s, but the rate is 0, essentially. Within the standard model, neutrinos are super duper long-lived. You could even have, in the standard model, you do have that. It's just stupidly small. Neutrino, neutrino, W boson, photon, and a lepton here. This is called a magnetic moment of the neutrino, and it is there. It is there. Standard model has this. But the size of that is just like, nope, you're not going to see it. Like, we are 20 orders of magnitude or 25 away from probing the standard model.
Yep.
So in principle, neutrinos do decay, but not enough in the standard model. Now you need to come up with a new physics origin, and the mass and the decay rates are not connected one-to-one because you have couplings and stuff.
yeah, no, I understand that we are 20 orders magnitude down to see that in Earth, but how far a source has to be for this to become something?
So the analysis is not that trivial.
Okay.
And here's the reason. There is a distance of the source. And for example, we have seen that, oh man, this is a great slide. So I didn't do this slide, but it's a great slide. We have seen events, a few, where we observed neutrinos coming from a specific object with a photon signal associated to that. There's this famous Texas TXS0806 something something, whatever that is. And this, I think this is a neutron star black hole merger. And we have seen the combined signal of neutrinos and gamma rays. One needs to be a little bit careful because statistically this is very tricky. There is a lot of what we call look elsewhere effect, but we can discuss about that at some other point. But the deal is, for some of the sources, we know the distance, but the energy estimate is actually pretty bad. If you imagine, if you are like at very high energies, it's much more likely to get an event that is like a through-going muon. Just because you have more ice outside the detector than inside, and at very high energies, these muons will just cross the detector. They'll not stop. They'll not be absorbed. So then what happens is you see light from a muon that was created outside. So outside started emitting light, and you don't see that. Eventually, you start to see the light from this muon, but it exits and keeps emitting light that you don't detect. So the uncertainty on the energy of the muon is at the order of magnitude level, which will translate to an uncertainty on the gamma, right? Which will translate to an uncertainty on the neutrino lifetime. So it's a bit more complicated, but yeah. It turns out that this bound is not super duper great because the ultra high energy goes against neutrino decay, right? Like the higher is the energy, the less you want to decay. So you're working against yourself up to some extent.
More questions?
So some years ago, IceCube announced that they detect one neutrino from the resonance, the glacial resonance. But I was reading that the significance is 2 sigma, and around 2 sigma, and it's only one event. So I want to know your thoughts about it, if it's a strong claim, a solid claim, or what do you think about it?
So the main problem is the following. So they did detect a very high energy event, okay, at the 6 PeV-ish level. The main problem is the following. Well, there are two main issues, right? One is, given IceCube energy resolution, which is pretty bad because you're seeing part of the energy that a muon emitted from a neutrino interaction, and you gotta infer the neutrino energy. Given IceCube energy resolution, the enhancement on the number of events, because your bins are like this size, it's more like a factor of 3 only. It's not a factor of 1,000. Imagine this, right? Let me draw this a little bit more peaked. Imagine that this cross-section goes like this, but your energy resolution, you're summing up all the events in this bin. This is super high, but it's super narrow. So in the end, the enhancement that you get is about a factor of 3 only. Which means that if you expected one glacial event and you saw about one event, you also expected 1/3 non-glacial. You know, if you expect 1/3 and you see one, is not so far. Besides, there is a non-negligible chance that this event actually came from here or here, but because your energy resolution is not so great at these high energies, you just reconstructed elsewhere. So when you account for all that, then the significance is not like 5 sigma, right? The significance becomes more like 2.3, I think, sigma or so. So yeah, I think it's fair to say that we have seen something consistent with a glacial event, but I don't think we can claim that we have seen a glacial event, a glacial resonance. And more than that, it's hard to use that as of right now for new physics and stuff, because you only have one event and you don't even know if it comes from a glacial resonance. Yeah.
So I think, given the time, I think we should stop here and you ask more questions offline. So let's go for the poster session.